Hey there, and welcome back to Linear Algebra. We're going to get started in Chapter 2 in this video lecture, looking at the first section, 2.1, about linear transformations. So I'll tell you what the objectives are as you're looking at them. I want to define what I mean by a linear transformation. It's a function between two vector spaces that has a certain property or properties. And then mainly by virtue of examples, I want to show you how you can determine whether or not a given function is a linear function. All right, so we'll just get practice using the definition, I hope, in some interesting examples for you. And then we're going to end with some sort of elementary properties of linear maps that I'll sketch proofs of or try to write some careful proofs of it. Okay, so that's kind of what's on the docket. Let's get going. Definition, I've got it already written out here. So if you give me two vector spaces over F, that'll always be our context. Then by a linear transformation, so I'm underlining what I'm defining, a linear transformation, well, it's a function. First of all, it's a function, I'm calling it T for transformation. Book uses the same notation. And this function has two properties. Okay, the quantifiers are that for every two vectors x and y and every scalar a in the field, that first of all, T of a sum is the sum of the values of T, or as it's written there, T of x plus y is T of x plus T of y. So you can evaluate T through sums like that. People usually call that the summation or additive property. And then second, T of any scalar multiple of x, T of ax, is a times T of x. So you can pull scalars through this thing. So any function between v and w that satisfies those two properties is called a linear transformation. Or if you like variations, people also call it a linear map. I tend to be one of these people. The word map is easier to say for me than transformation. Or if I'm particularly lazy, I'll just say T is linear. So if V and W are vector spaces and I write something like this and say T is linear, it's a lazy way of saying T is a linear transformation. T is a linear map. Okay. These two properties separately, sometimes people will call this property T is additive. Right, so T sends sums to sums, and this property people say T scales. So it sends scalar multiples to scalar multiples. So a function that's additive and scales is a linear function. Let's look at some examples. Here the vector space V is R2, and so is W. So I have a function from R2 to R2. And I'm just giving an explicit formula for it. So what do I do to an element of R2? Here, A and B are any two real numbers, if you want me to be more precise. So for any two real numbers, A and B, T of A comma B, which is an arbitrary element of R2, is given by that expression 3A plus B comma A minus B. So I claim that's linear. Oops. T is linear. So to show it, well, we have to take two vectors. Let's let, say, x equal vector in R2 looks like a pair of real numbers. Y is the same. I need some other pair of real numbers. I think I'm going to take, I don't know, C and D. And then I need a scalar. I've already used the letters A, B, C, and D to denote these things. So for a scalar, I'm going to say let R be a real number, my scalar. All right? And then I'm just going to check the two conditions. T of x plus y. I don't know how to evaluate T until I have it in the form of a pair. So T of x plus y, well, x is the pair A plus C, comma B plus D, right? And now I can use this formula for T to apply that. So T of a pair is, well, you take 3 times the first coordinate plus the second coordinate. And then in the second coordinate, you take the first one minus the second one. All right, so I just have to do a little bit of algebra here. What have I got? 3a plus 3c plus b plus d, comma a plus c minus b minus d. And now I could work out T of x plus T of y separately, but I think I'm just going to kind of keep going in the forward direction here. So I'm going to write this as 3a plus b plus 3c plus d, comma a minus b plus c minus d. You certainly agree with the algebra, and you can probably see where I'm kind of going with this, because that to me looks like the pair 3a plus b comma a minus b plus the pair 3c plus d comma c minus d. Yeah, and that precisely looks like t of ab plus t of cd, and that's precisely t of x plus t of y. Good. All right. So there's a computation that t of x plus t of y is equal to t of x plus y. I think I'm going to leave it to you. This is a good breadcrumb trail. You show that t of, what did we call our scalar? Rx is rt of x in the same way. Right? So what do I mean by the same way? You have a coordinate expression for x, you know how to multiply it by r, then take t of that, and then so you get the same thing as if you multiplied t of x by r. Right? So that's a linear function. Cool. Let's look at another example. This one is a little bit more general. So it's a vector, a function from Rn to R, right? So n here is some whole number that's greater than or equal to 1. And then I have a function, I'm calling it pi j. So if you like, this is my t. Yeah, so I'm giving it a specific notation because we're going to be using it throughout the course. But I'm defining a function from Rn to R, but I'm not calling it t, I'm calling it pi sub j. Pi is kind of phonetic for projection, and the j here is projection on the jth coordinate. So I've written a formula there. Pi j of x is xj. What do I mean here? I mean x is a vector in Rn, so it has n coordinates, all of which are real numbers. So that makes this formula make sense. What does pi j do to an x? It just sends the vector x to its jth coordinate, right? And I claim that's a linear function. It's a linear function for every j. Why would that be true? I'm going to to keep this video a little bit shorter. I'm not going to quantify all my variables super carefully here, but if I wanted to look at pi j of, say, x plus y, okay, well, I know what the jth coordinate of x plus y would be. It would be x sub j plus y sub j. And that's precisely pi j of x plus pi j of y, right? Pi j is additive because of the way we add vectors in Rn. Nice. Likewise, if r is a real number, pi j of rx, well, what's the jth component of rx? It's r times the jth component of x, and that's precisely r times pi j of x. So it's an important function called the projection onto the jth coordinate. Okay, so there's n of those things in Rn. Cool. Let's look at another example. This time my vector space V is the m by n matrices, yeah, m rows and n columns. W is the n by m matrices, n rows and m columns. And I'm not even defining, or not naming rather, the function this time. I'm not going to call it capital T. This is an alternate notation. I'm just saying that a matrix A that's m by n, I send it to its transpose. Remember that notion from before? The transpose. And the transpose of an m by n matrix is certainly n by m, and it's linear because of properties of transpose. If you take two matrices and you want to look at the transpose of their sum, we proved before, or we discussed, that that's the sum of the transposes. That's the additivity. Likewise, if you take a scalar, I'm going to stick with the letter R here for this lecture, you multiply every entry in a matrix by the number R, well, you could certainly take the transpose of that matrix and then multiply all the entries of it by R, and you would get the transpose of the matrix A multiplied by R. So there's your scale, right? So transpose is a linear operation. Transposing a matrix is linear. Neat. Here's kind of a calculus-based example. I'm calling my function this time d. I won't call them t always. T is the kind of generic name, but d of a polynomial of degree less than or equal to n is its derivative. Its derivative like with the power rule, yeah? So for example, if you wanted to take d of something like x squared plus 2x plus 11, well, just like in calculus, that's 2x plus 2. Right? So you take a polynomial of degree at most 2, and you get a polynomial of degree at most 1 when you take its derivative. Yeah. And why is d linear? Well, if you take two polynomials, their degrees are less than or equal to n in particular, and you want to take d of their sum, well, that's the sum. It's derivative of the sum, and from calculus, or you can even prove this algebraically for polynomials, but the derivative of a sum is the sum of the derivatives, yeah? So that's equal to d of f plus d of g. So that formula that you learned in calculus, that the derivative of a sum is the sum of the derivatives, that's just the statement that the differentiation is an additive operator. It's an additive map. Yeah, so on the vector space of polynomials in particular, or even differentiable functions in more general, but here I'm talking about polynomials. Same, the scalar multiplication property. If R is a real number, right, you know as well as I do that if you're going to take the derivative of R times a polynomial, you just multiply the derivative of that polynomial by R. So again, that familiar calculus property is just scaling. In fact, that's the whole point of this example, is those familiar properties in calculus. The derivative of a sum is the sum of the derivatives. You can pull constants through a derivative. In linear algebra language, those properties are, oh, differentiation is a linear map. Differentiation is a linear map. Here I'm specializing to polynomials, and so there's just one more little wrinkle in the story, that the derivative of a polynomial is also a polynomial, right? But you could replace, in this example, polynomials with differentiable functions. Over here, make this continuous functions. The differentiation map is a linear operator on those vector spaces. Cool. Here's another calculus-based example. Same kind of thing. I'm going to actually keep this kind of brief, but here my map is called I. I is for integral, and its value on let me remind you that this is the set of continuous functions on 0 to 1. So let me remind you of that. C01 is the set of those functions whose domain is 0 to 1. Its codomain is the real numbers, and they're continuous. So continuous functions on the closed unit interval. You remember from calculus that every continuous function has a Riemann integral. That's a number. So this function's value I on a continuous function is the integral of that function from 0 to 1. All right? And why is it a linear map? Well, because of calculus properties, like if you're going to integrate f plus g, you can integrate f and g separately. The reason I'm mentioning these examples is to kind of point out to you that lots of places in your mathematical career, these properties that you learned, here I'm pulling a constant through an integral, those were just statements that there's some linear map running around. Integration is a linear map. It's additive and it scales. So you should pause the video and kind of think to yourself, are there other places in mathematics where you've seen these phenomenon that like doing something to a sum can be done term by term, doing something to a scalar multiple can be done before or after you scale? Because if you can think of an example like that, then you're thinking of an example of a linear function. Nice. The sixth example is kind of just some generic ones. This function, I'm going to follow the book's notation and call it T sub 0. Its domain can be any vector space. Its codomain is 0. And it sends every function to every element of V to the 0 vector. All right, so we're just going to call this 0 map, 0 function. And I'll leave it to you as an exercise, but it's linear. The zero map is additive in scales. Likewise, there's one other special function, some notation, 1 sub v, oops, sorry about that, if v is a vector space. 1 sub v just denotes the identity function. So for every x in v, 1 sub v of x is x. It's called the identity function or the identity map. Again, I'm going to leave it to you as an exercise. Both these maps are linear. Both of those things are linear transformations, linear maps, linear functions, same thing. Okay, let's look at some properties. Properties of linear functions. I'm going to kind of quickly sketch some proofs of these things. So everywhere, V and W are vector spaces, and I've got a linear function. So that's kind of the preamble. And there's more than 3 properties of linear functions, but I'm going to focus on these 3. The first one is that linear functions have to send the 0 vector to the 0 vector. So that's a good way to show that a function isn't linear, for example. Maybe, well, we can, so if somebody hands you a function and they're asking you the question, is this function linear? One of the first things you can check is like, well, does it send the 0 vector to the 0 vector? Because if it doesn't, it can't be linear. Nice. Another one for any 2 vectors, sorry about that, for any 2 vectors x and y, t of a difference is the difference of the t's. That follows from linearity. And then this third one is kind of just an inductive. If you take a bunch of scalars and vectors, n of them, you apply t to their sum, well, then you get the sum of the scalars times t of the values. So it pushes through more than just one sum. All right, how to prove those things? Let me sketch, say, this first one. To show t of 0 is 0, I'm going to take advantage of the fact that 0 is plus itself. But by linearity, t of 0 plus 0 is t of 0 plus t of 0. And then what am I doing? I'm going to apply the cancellation laws. Cancel t of 0 from both sides, and you get, well, 0 is t of 0. Nice. I didn't leave a lot of room for an example of a function that's not linear. Maybe I'll squeeze one in at the end. Nice. How about the second one? How to prove t of a difference. I didn't quantify this. I'm just going to kind of walk you through it real quick. If you're looking at t of x minus y, well, you just have to think of x minus y as x plus negative 1 times y, right? So now using the linearity with this plus, that's t of x plus t of the other thing, minus 1 times y. But then bring out that scalar. Right, t is linear, so the minus 1 can come out front, and minus 1 times t of y is just minus t of y. Third one I'm going to leave to you. It's a nice exercise. Induct on n. Induct on the number of terms in the sum. Come to an office hour, talk to me about it. We'll write out an induction proof together. Maybe I'll do it right here, since there's a teeny little bit of room. If I took a function, say from R2 to R2, and I say t of AB is, I don't know, a plus b plus 1, comma, a minus b. It's not linear. Which might surprise you because you're looking at those coordinate functions, a plus b plus 1, a minus b, they kind of look linear. But look, t of the 0 vector is not the 0 vector. So I'm not going to check a bunch of properties about that t. It can't be a linear map. Yeah, so this is kind of a nice thing to check right away. Is somebody hands you a potentially linear map, what's it do to the 0 vector? If it doesn't send it to 0, it's not a linear map. Cool. Okay, one more result in here I want to prove as a theorem. It's just a property in your text, so it doesn't have a number. But it's just kind of a one-step criteria to show something is linear. So it's an if and only if theorem. And the conditions are, well, you're linear if and only if, for any 2 vectors and any scalar c, t of this linear combination, cx plus y, is c times t of x plus t of y. All right? So that's what I mean by this condition. So one direction of this theorem is trivial, that if t is a linear map, let's get rid of this first direction first. If t is linear, Well, then if you take two vectors and a scalar and you apply t to cx plus y, well, by linearity, that's t of cx plus t of y, pushing it through the sum by additivity. And then by the scaling factor of t, you can bring c out. So that direction is kind of trivial, that a linear function has this property, right? When you go to do your induction proof, you'll use similar ideas for your base step. So really, we have to think about the other way. So why would a function with that property be linear? So let's suppose that t has this property. T maps v to w, and for every x and y and every scalar c, t of cx plus y is c times t of x plus t of y. Okay? So we just make some judicious choices. If we take c to be 1, because it's true, remember, this is true by hypothesis for every x, y, and every c. So in particular, I can take c to be 1. Then for any xy, since c is 1 and 1 times a vector is the vector, t of x plus y is t of x plus t of y. So there's the additivity. This thing, t of x plus y is t of x plus t of y, it's the only property of linearity that we use to show that t of 0 is 0 above. So that same property, we know, implies that t of 0 is 0. So if I take y to be 0, then for any x, if I look at t of cx plus 0, that is t of cx, well, then by the property I'm assuming for t, that's c of tx plus t of 0, but t of 0 we said is 0. So you just get c times t of x, so the thing scales. Okay? So this is, if you like, it's kind of a one, instead of checking conditions 1 and 2 for linearity separately, if you want to, you can just check this single condition. So if somebody's asking you to show a function as linear, you can take any scalar and any two vectors and show that this boxed formula holds, and then you're done sort of showing the two steps of linearity in one. Okay, so that accomplishes our goals. I'm just going to kind of flip back to the top of this thing to make sure I didn't leave anything out. But what I tried to do was tell you what I mean by a linear transformation. So I hope I've done that. I hope I'm giving you some some ideas of how you show something is. You verify those two conditions or the single condition in our last theorem. We had 6 examples. We'll have lots more. And we looked at some properties of linear maps. And in particular, we kind of discussed how you might use them to show something isn't linear. Okay, so I'll stop it there and thank